Hi, my name's Russ. I'm going to talk about clean burn patterns and color changes in fire. This is meant to provide some tools for forensic analysis of fires, mainly focusing on trying to provide more information for defendants in both criminal and civil litigation. So, fire forensics are the tools, the body of tools used to analyze fire conditions, try to identify source, how it behaved, perhaps why a structure didn't have its life safety features function correctly. Um, just tools to basically re-engineer a fire. So I'm going to talk a little bit about clean burn. What clean burn is, it's where you have the soot that was deposited on a fire burn off, and what you have on cooler surfaces is soot is going to condense, almost like water condenses on a window. It's the same principle, only at higher temperatures. And clean burn is going to occur where there's higher temperatures, so it can be used to identify an origin. But unfortunately, there's some biasing that can occur given certain fire conditions. So things to consider, this is a snipping from the former image, and it shows just a portion of it. This portion was influenced by suppression. So the very nature of taking a hose stream and putting a fire out, it's going to wash soot away. So even though the former image did show clean burn on the periphery, this clearly has indications of suppression, biasing that clean burn. Here's also another situation. The OSB put up here to cover this window, obviously not there when the fire occurred, but when this window broke, what it did, it is allowed oxygen access to these surfaces. And that oxygen enabled a hotter, cleaner burn that resulted in these clear areas, these clean burn areas. So both ventilation, temperature, oxygen content, as well as suppression can influence the appearance of clean burn areas. So here's an example of how it actually worked. What you can see is this clean burn area in the middle where the temperature was higher, surrounded by the sooty deposition. So what happens in fires is that when you have fire above 1,000 degrees Fahrenheit, when there's ample oxygen, what'll happen is it'll produce clean burn, and it actually can burn off existing soot that is on walls. So soot adheres to cooler surfaces. Soot burns away from hotter surfaces. Here's an example of a fire cell that was put together to demonstrate this principle. And what you had is over in this corner, if you look at the image in the bottom right left, that corner is the source of fire origin. And what you see here is there is some clean burn in this area. Also on the ceiling, there's clean burn, there is suppression, indications of suppression damage to the soot there. And then over on this side, on the bottom left, what you can see are some ventilation effects on the ceiling. So where this came from, if you look at this cell, this was put together. This is basically the cells that we just looked at. And the fire is in the corner. Don't be deceived, this is a mirror. It was put there simply as a furnishing. But this is an image taken just nearing flashover. This is at flashover conditions. And so the results, when they came in and cleaned, um, this is what you ended up having. But just looking at this, if you were looking at this, it'd be really hard to identify the origin from the clean burn patterns. You might think it's over here, but it was actually in the corner, as we previously noted. So, multiple tools have to be used in identifying the origin. A clean burn alone probably is not sufficient in this case. And this is an FDS version versus a real-life simulation, just to demonstrate this principle. In this case, so the image on the left, the fire actually happened in this compartment at the top right. Now, this is fire dynamic simulation. This is a computer model. But what happened was there's this door that's on the bottom left of this left image. That door was left open for this FDS simulation, this fire dynamic simulator analysis, and it allowed air to rush in. And if you look over on this side, look at the clean burn on the right side, on the other wall, the wall opposite of this door. Now that clean burn is from the ventilation effect. The air rushing in produced cleaner, more oxygen-rich air, burned hotter. So you saw the soot deposition taken away on the opposite wall as well as the ceiling. And if you look back at the origin of where this fire happened, you don't see the clean burn here. So what happened here in flashover conditions, you had, you know, more heat here, a cooling effect here, and soot deposition where there may well have previously been clean burn patterns. So here's an example of suppression influenced appearance that looks like a clean burn. You can see it's splotchy and it's smeared. So this is where a hose stream hit the wall, hit an otherwise sooty wall. I want to talk really quick about color changes. So in this case, you have paint that was influenced by a garage fire. So the garage fire was over on the right, rushed flames out over this car. So you see some influence here, and on the hood, but there's clearly examples here where the paint was discolored. The principle here is the polymers that make up your paint, they actually change under exposure to heat, and they actually reduce in size, and that changes their light refraction properties that modifies the color of that paint. Here's an example of concrete. What's interesting about this is you have polished concrete. The one on the left side, that was your control. That was at normal ambient conditions. The one on the right side was kept at 350 degrees Fahrenheit for an extended duration. And what happened was there's clear color differences in your aggregate as well as the Portland cement matrix. So one thing to consider with these principles of heat-induced color changes, I think many of us have left a shirt or a hat outside on a summer, maybe even prolonged summer days. Leaving it out there, let's say for a month, you go pick it up, you notice that it's changed color. So the very nature of being subject to solar intensity, it changes the color of the dyes that are in that cloth. You could say the same thing about chemicals such as exposure to pool water. So make sure not to misinterpret color changes that may be associated with heat due to fires, when in truth they're actually associated with natural processes or introduction of chemicals to the environment. Oxidation is kind of interesting. Here's an example of galvanized steel that experienced some high heat flux over time and resulted in oxidation. There's clearly a line of demarcation where the solar or the heat flux from the fire occurred that shows you how the transition for galvanized steel between normal galvanized steel and the oxidized surfaces. Other materials have this similar effect. If you look at copper on the left, copper has a black oxide associated with it. Now this stainless, you don't normally think of stainless steel as oxidizing. It's pretty robust, but at high heat it does form a gray oxide, which is shown here from a garage fire. This is an interesting experiment too that demonstrates the effect of chemicals and temperature over time on carbon steel. So in this case, you have 5 samples that were exposed at ethanol-containing gas at 500 degrees Celsius. And there was different times that this exposure occur, ranging from 30 seconds on the left to 240 seconds on the right. Now, if you looked at this under a very sensitive microscope, you can see serious topographic differences between the various samples. And that's another mechanism that underscores the changes due to this color oxidation, even if it was an oxygen-rich environment. So that's it for my presentation. If you have any suggestions or comments for me, feel free to let me know. Thank you.